Hello, I was doing videos for all my other classes and I didn't want you to think that I didn't care about you or that you'd be like, man, we didn't get any in physics. So here's a little video clip on the two new things I asked you to do on the electricity unit. I know you're worrying about your test that was supposed to be today and it's going to be tomorrow, but exams are coming, so we still need to continue on. So the two sections I asked you to work on, which will really be for Friday, are the one on the back side of your sheet, resistance, and then on power. So resistance first. So yesterday we were already talking about resistance, and we talked about the fact that it comes into play in Ohm's law, V equals IR, R is equal to V over I. So resistance is measured in volts per amp, which we call an ohm. And so everything like light bulbs and televisions and ovens and dryers, they all have resistances. But today, the part that we need to look at are the wires themselves. Yesterday, I said everything has some resistance, and that includes the wires. So think for just a minute, what do you think the wires, which are the conductors, their resistance is going to depend on? And really, there are four factors. One factor, and these are all in your notes, but I'm just going to go over them because maybe it'll make more sense. One factor is the length of the wire. And that should make sense if you think of resistance like friction, because the length of the path that an object travels is going to matter for friction. So of course it would matter for the wire too. The longer the wire, the more energy you're going to lose to resistance. And so if you're creating a circuit, you don't want to have wires running down to St. Mary's supermarket and back. You want the smallest length of wire possible so you don't lose as much energy to resistance. So one factor is wire, length of wire. The second factor is what's called the cross-sectional area of the wire. The cross-sectional area. And really what that means is how big the wire is if you were to look at the end. Maybe it's really large, maybe it's really tiny. How big it is going to determine the resistance. It should make sense to you that the bigger the wire, the less resistance, because the more the current could flow through the center of the wire and not rub on the edges. Whereas the wire is tiny, it's going to rub on the edges, and it's going to, the current is, and it's going to lose more resistance, to more power or energy to resistance. So cross-sectional area. Now to find the cross-sectional area, you would need to find the area of the end of the wire. It's obviously going to be determined or dependent upon the radius. Area, for most wires are circular, would be pi r squared. Okay? Now cross-sectional area is often, when we talk about size of a wire, you'll often hear people talk about gauge. The first time I went to buy wire, the buddy at the home hardware store said, "What gauge do you want?" I looked like I must have been stunned. I didn't tell him that I was a student and studying for my master's in physics because I didn't have a clue what gauge was. I was like, Anyway, I went home and phoned my father, and then I went back and knew what I was talking about. But you'll hear about 8 gauge, 10 gauge, and that gauge then is connected to cross-sectional area. And if you go to page 708 in your textbook, there's a little chart right up here, okay? And it shows you the gauge of the wire and the diameter in millimeters. Ignore this third column, we won't use it. But if it ever tells you in a question that a wire has a gauge of 10, then you go to this chart and you find out that means it has a diameter of 2.59 millimeters. So then you would use that diameter, change it to meters, divide it by 2 to give you the R, and then find the area. Okay? Notice that as the gauge gets bigger, the wire gets tinier. Clearly, I didn't make this up because I would have done it the other way. So as the bigger the gauge of the wire, actually it's the tinier the wire. So the second factor then that resistance of a wire depends on is the cross-sectional area, often referred to or connected to the gauge. The third and fourth factor are kind of together. because the third factor is the material itself, right? Whether you're using copper or glass or thread. So the material itself. Obviously, the more metallic something is, the better the conductor. And so the lower the resistance. The compounds and things we said yesterday and non-metals are poor conductors, so the higher the resistance. So the material itself has, remember how all surfaces had a coefficient of friction? Well, in resistance then, there is also a similar constant like that, and it's called the resistivity. It's a Greek letter as well. It's a Greek rho, so a fancy script small p, and it's called the resistivity. And there would be a chart that you could look up the resistivity for particular materials. It happens to be on exactly the same page as the chart for the gauges. Okay, so here's the chart for resistivities. So you'll see it for silver, for copper, for aluminum, etc. Okay, notice resistivity is measured in ohm meters. Okay, so it's resistivity. And if you look at the very bottom of the chart, it says the values are given for a temperature of 20 degrees Celsius. And that's because the fourth factor that resistivity is dependent upon is temperature. Okay? Because the higher the temperature for a metal, the poorer the metal is as a conductor. That's why our rooms with the computers are air conditioned. So metals increase their resistance as the temperature goes up. It's the exact opposite for the non-metals. The non-metals actually have become a better conductor when the temperature is higher. Okay? So these are the four factors that affect the resistance of a wire. The temperature will actually hide out inside the resistivity. So the chart I showed you a minute ago was for a temperature of 20 degrees Celsius. If the temperature was 40 or 50 degrees Celsius, you'd need to go to a different chart because the resistivity would change. So from these factors, we can get an equation for the resistance of a wire. It's R is equal to rho L over A. So rho is the resistivity that you'll look up in a chart or be given. L is the length of the wire, and then A is the cross-sectional area that you will find by just simply doing the area. You might need to go to the gauge page chart to find the diameter, which would then give you the radius, and then change it to meters, and then stick it in to get the area. Okay? And so there were questions on page 708, questions numbers 16 to 20, with this equation that I would like you to do for Friday. What's probably going to happen tomorrow is that I will give you the answers to all these homework questions, so when you come in on Friday, you can tell me which ones we actually need to do. Now, for these questions, you're going to need the chart on the two charts on page 706, okay? So go to the charts on 706 to get the constants for these questions. All right, next up is power. That's the other sheet that I asked you to look at. Okay, power. Okay, so now from grade 11, we know that power is equal to work over time. Okay, and this unit, last unit, we had the equation that V was equal to W over Q. So that means work is equal to QV. So if we take this and fill it into our power equation, we get QV over delta T. But look, Q over delta T. We learned just the other day that that's current. So power is equal to IV. Easy way to remember it. If you're weak, not feeling very powerful, go to the hospital, they'll hook you up to an IV and you can get more power. Units, this would be an amp times a volt. And an amp times a volt, we have renamed a watt. Power is measured in watts. Now your textbook goes through like 4 or 5 sections and comes up with other equations for power using Ohm's law. V is equal to IR. Because if we take this and stick it in up here, then we get power is equal to I squared R. So that's the second equation. And then they rearrange this and they say, well, I is equal to V over R. And if you take this and stick it into that equation, then you get power is equal to V squared over R. So both of these equations are other equations for power. I usually use this one and then derive these as I need them rather than try to memorize all three, because I'm pretty sure you know V equals IR, so you can just sub it in. Okay? The one other thing that we should talk about is energy, as it's on your sheet as well. Energy. And we know that energy is really the work done. So back up here, right? V is equal to, remember, EQ over Q. And so energy then is going to be equal to, or actually maybe I'll even go here. This power is the same thing as EQ. So not this one. Let's do a new page. Let's do power is equal to work over time. And really that means power is equal to EQ over time. So energy, EQ, electrical energy, then is just equal to power times time. This is what you buy from a power company. New Brunswick Power does not sell power, it sells energy, because it's all about how long did you run your appliance, not just how much power it takes. Okay? And so we would measure energy. We know power is in watts and time is in seconds, and a watt second would be equal to a joule. But if you look at your parents' power bill, you will see that it's not in watt seconds or joules. It's in kilowatt hours. And that's because this is too tiny of a unit for them to use. So we would go from watts to kilowatts by dividing by 1,000. And we would go from seconds to hours by dividing by 3,600. And so there's going to be some questions in the set of questions that's shown on your page of power where it's going to ask you to find the energy in kilowatt hours. Okay, so when we're calculating energy, like how much energy did your clothes dryer use to dry your jeans, it'll be in kilowatt hours. Because then there's an equation where you can figure out then what did it cost you to dry your jeans or to dry your hair. And the equation for cost is just the rate that the electric company is charging times the energy that you're using. Okay? So on that page with power, your power notes, there are a whole bunch of questions here. They're all really pretty pathetic. Okay? But you do need to try them to get the practice. And there's one other thing up here that I note, and it says, when the current changes, the voltage changes, and vice versa, but R stays the same. You need to be careful of that when you're using these power equations. So if the voltage doubles, and it says, what's the new power, it's also going to cause the I to change. So you have to find the new I before you can find the new power. Anyway, but as you do your homework questions, you'll discover that, and it'll give us something to talk about. Okay, so please try these questions for Friday. Tomorrow I'll give you a whole bunch of answers so that you can check them. All right, see you tomorrow.